topic today, which is how to do broadcast and reductions efficiently. So we're going to talk about that, and then we're going to talk about interconnection topologies in the second half of the course. So we're going to use this so-called alpha beta model for performance, and maybe if we need to refine it, we'll make a note of it someplace, but mostly we'll use the alpha beta model. Do you see any issue with the alpha beta model, by the way? Alpha beta model being what? That if you want to communicate from place A to place B, processor, one processor to another processor, as long as it's a remote processor, I don't care which one, the cost is going to be number of messages, like alpha times the number of messages plus beta times the reciprocal of bandwidth, cost per byte, right? And any algorithm, the completion of the time of that algorithm can be understood or can be calculated based on this. That's the hypothesis, based on this simple cost model. Where do you think it runs into trouble? Yeah, right. It can account for overlap. It depends on how you do the analysis. So you can write it so that with the max operator, so that you say, while this message is going on, this computation is going on, therefore I can take a max of those two. So you can handle that. Yes. Yes. Correct. It does not consider topology. It does not consider capacity contention in the communication network. Whatever the communication network is, I'm saying if I can talk to you at this bandwidth, I can talk to you at the same bandwidth even if other people are talking to each other at whatever rate they are talking. So in other words, we are assuming there are dedicated communication resources between each pair of processors. In reality, that's not true, and so that adds that makes you sometimes have to do an analysis of contention separately, and we'll come back to that when we talk about after we talk about topology. The some other ways of, or some other constraints are injection rates. Like I can talk, I may be sending a message this way, I may be sending a message that way, a third message that way in the topology, completely different communication paths, but they still have to go through my internal hardware, which is the gateway to get to the communication hardware to send it to other places. So that leads to limitations on injection bandwidth, so-called. But we're going to ignore those effects for this analysis of broadcast and reductions and algorithms for broadcast and reductions that we'll talk about now. So just to remind you all of terminology, scalar reductions are reductions where everyone has one number, and the result is the sum of that. It is made available in one place. That's just a regular scalar reduction, right? So P0 or whatever is the root of that reduction gets the sum, which is 3 plus 2, 5 plus 12, 17 plus 9, that's 26. So of course, instead of sum, it can be other commutative associative operations, or it can even be associative operations in some cases. The other type of reduction is a vector reduction, where everyone contributes a vector. Instead of contributing a single number, they contribute an array of numbers. So 0 contributed 3 to 7, 1 contributed 1 to 7. I'm just picking integers, but it could be floating point numbers or double precision numbers, and so on. And in this case, a vector reduction means the sum of the corresponding elements of the vector. So 3 plus 1 plus 4 plus 7, those are the first elements. So that gives you 4 plus 4, 8 plus 7, 15. That becomes the first element of the array. Similarly, 2, 2, 5, 8, that becomes 10, 15, 17, becomes the second element of the array. And the third element added together becomes the third element of the result array. And so the result is again made available only in one processor. So this is a vector reduction. So we're going to talk about how to implement vector reductions or reductions, scalar reductions efficiently. The third variation, which is basically third and fourth, is that for both vector reduction and scalar reduction, you can say the result is available not just at one processor, but at all processors. So this is an all reduce, where you need the sum, but you need the sum available on all processors. All right. Now, these operations are not magically implemented by MPI. MPI is not hardware, so it is going to implement them using your point-to-point, using your processors in some fashion, right? So let's say, can we think about point-to-point algorithms for implementing these operations? And does that sound familiar? Because you did one question like that in the exam, right? So, yes, but so no further knowledge than what you learned before the exam is needed to analyze an algorithm, but we're going to come up with 2 or 3 or 4 different algorithms and compare them and see what kind of issues are involved in implementing these efficiently. Okay. And in fact, broadcasts and reductions are somewhat symmetric in nature. If you can broadcast in one fashion, let's say along a spanning tree, then it can reduce along that same direction. Just that in reduction there is an operation to be performed. In broadcast there is no operation, it's just the data that's moving. In reductions you may be summing or maxing or whatever it is that you're doing. So in a reduction, a naive algorithm is everyone send their data to P0. It's very natural for you to implement, for beginners to implement reductions when they don't know about reductions by doing, oh, let's just send the data to 0. It's fine. What's the problem with it? Where in the cost model do you see the problem? It is the alpha plus n beta, whatever the data size is, for receives on processor 0. There's alpha plus n beta at the network, at the sending side, but those can all happen in parallel in principle. But at the receiving side, there is some, and these are different values of alpha and beta. So alpha for receiving the message on a CPU cost might be different than the alpha for network and the alpha for sending side, and same for beta, right? So those alpha beta are just the constants that the machine provides, the machine has for as costs of various things. But the cost here for receiving the data on root processor is a problem because it's going to be serialized. The root CPU cannot do all those P things in parallel, so it is going to receive one, add it, receive the second one, add it, and so on. And so that cost is going to be order P cost, and that's a problem when you have thousands of processors. If you have just 8, it's probably okay to do this. But if you have hundreds of processors and thousands for sure, then you want to do it differently. And a different way of doing it is just organizing processors in a k-array tree. So the branching factor of the tree is k. How do you decide which processor goes at what place in the tree? We don't have any, our basic assumption is going to be every processor can talk to every processor at equal cost. So if I'm processor 23, then the cost that I incur in sending a message to processor 24 is the same cost that I incur to sending a message to processor 129. That's going to be the assumption, and later on we'll see if we can change that assumption. It works in most situations than you might concede. In other words, if in fact on a real machine today, if I send a message from here to here and it goes through these intermediate processors on organized in a, let's say, 2-dimensional mesh or 3-dimensional mesh, it is going through various switches at various points, but actual delay for the message going from here to there is about the same as the delay of it going to the next processor. And the reason for that is something called a wormhole routing. And wormhole routing is where if I send the data to someone, if I send the data to you and it is going through these 2 hops along the way, then I don't send the entire megabyte of message to you, then you send the entire megabyte message to the next one, and so on. I send it flit by flit, I send it packet by packet, and even each packet doesn't get sent in its entirety to the next processor. I just send the first few bytes of it, 2 bytes or whatever is the width of the network. It's called a flit, which is just maybe typically 2 bytes, and I might send those 2 bytes to you, and those initial bytes may include the description of where it is going. And so you know whether to send it left or send it behind, and you send it there, you reserve that channel, and then on my bytes are coming to you, flits are coming to you, and you are just pushing them to the next one. It's like a train or a worm moving through the whole network, right? And so if it gets blocked, the whole worm gets blocked, but if it doesn't get blocked, then the whole thing keeps moving, and then it gets delivered to the end processor. You can imagine, except for the delay for the first byte, that until it reaches there, that delay, all other stuff is pipelined. So you're just going to get 1 byte delivered, 1 flit delivered every clock cycle after that. And so this is a reason why for a variety of situations, we will say that it doesn't matter. Let's ignore, do the first order analysis where you ignore any kind of interconnection topology and so on. We'll later on get into more detailed analysis of that. But for now, our assumption is interconnection topology doesn't matter. Given that assumption, how do you decide which processor goes where in the tree? It doesn't matter, is the first order answer, right? Because everyone connects to everyone else with equal efficiency. Or it doesn't matter, that's fine, but I still need to know who my parents are and who my children are, isn't it? From a parallel algorithm that depends on a tree structure, every processor, every rank needs to know who his parents are and who his children are. For now, again, we're going to assume an MPI plus OpenMP type thing where there is a single MPI process on a whole host, an entire node, right? And all the multiple cores within it are used using OpenMP, right? So given my rank, who are my children, who is my parent? Does anyone know some simple scheme for doing this? Yeah. That's right, you did it in the exam. I was trying to think you would remember. Anyways, if you have k array tree, then your children and your rank is x, then x times k plus 1, x times k plus 2, up to x times k plus k are your children. 0, and the reason it doesn't begin with x times k is because you start with 0, your child is not 0, it's 1. So 0 times k, that's 0, plus 1, 2, 3, 4 up to k. So the next k guys are your children, and each one of them claims the next k children, and so on. That's how that goes. And so that's very easy to organize, and then your parent is easy to figure out by just dividing, well, subtract 1 and divide by k, and you have the parent's ID, right? So you can find your parent's ID and children's ID, and then you can just basically, you're doing a reduction. So everyone send, if I'm a leaf, I'm just going to send it to my parent. How do I know I'm a leaf? My children's IDs are outside the range. They're larger than the max number of processors. And so then I'm a leaf. I send my contribution to my parent processor as a point-to-point message. It waits for all its children to send, get their messages, and then it adds them up, or whatever reduction operation we're doing, and then add your own data and send it to the parent. And if I'm at the root, then I'm done. Now the question in this algorithm is, what is a good value of k? What branching factor should we use? 2, 3, 4, 10, log p? How do you go about analyzing that? Well, the way you go about analyzing that and deciding that is by writing an expression for the completion time of this algorithm in terms of k, and then trying to find when it becomes minimum, right? So now if you look at a simple analysis, each message, let's say you're doing a vector reduction, vector is of size n, so alpha plus n beta is the cost of each message. Now you're going to get k messages at each level of the tree, right? Each internal node is going to get messages from its k children, right? And then it's going to send one message up. So let's just say k messages, right? Could say k sends and k receives and one send, but let's just say k. It's a small difference there. I probably should put k plus 1, but k multiplied by number of levels of the tree, which is log of p to the base k. So log p to the base k multiplied by k times alpha plus n beta. This is a constant, right? This is just machine constant, and n is the size of the message that you're dealing with. So once those are given, you just want to minimize this expression, right? So your choice is only k, so it doesn't matter what this is. So some k log p, what is the minimum value of k log p? Anyone remembers from anything? Well, how do you find this? Well, you can differentiate and equate to 0, or if you are a computer scientist, you put it in a spreadsheet and look at several values and say, oh, that must be that. But anyone has a guess where that's going to be? The thing is, the first term increases as k increases, obviously it's k, and the second term decreases as k increases, because log of 1024 to the base 2 is 10, log of 1024 to the base 32 is 2. So it's the second term decreases dramatically with k. So where do you want it? Any guesses? Any solutions? Differentiate and equate to 0 to find the minima. Whatever you want to do. K is the variable, remember. Even guess is fine. How much does it depend on p? Of course, for very small p, you want to just use some constant, doesn't matter. But for sufficiently large p. So let's compare binary, right? One extreme. If you make k equals 2, it becomes 2 log p to the base 2. If you make k equals 4, it becomes 4 log of p to the base 4. And those are what? The same, aren't they? Because that's log of p to the base 4. Here you got a factor of 2 extra, but you take away a factor of 2 extra from there, so it's same. So in fact, the minima is something like 2, 3, or 4. Okay, and I'm not going to go into the detail of that, but small branching factor works. Maybe 4 is better than 2 for some second order reasons. So you can pick some kind of a value for k, a small value for k, and that will be your algorithm. So this is just an example of how to go about analyzing and optimizing your algorithm using the alpha beta model. Now, of course, broadcast is similar to reduction, except you're coming down the tree rather than going up the tree. Now, the interesting thing is, here's a calculation. If p is 1024, k is 2, k is 4, it turns out to be the same. And so, in fact, k is 3. That's kind of odd, but what is 3? Will 3 give you a better value or not? I have a feeling that 2 and 4 are better than 3, but you can just, that's an empirical experiment. I don't want to do this differentiation right now, and it turns out that if you do larger values, the k being larger costs you a lot more than the reduction in this, so you don't want to go there. Okay, but if you look at this, what is happening? What is happening in the reduction operation? All the leaves start 1, 2, 3, 4. 4 messages get, I mean, these messages get sent, but then these links are doing, these processors are doing nothing, right? This processor is doing nothing. This is receiving, but if you consider all the processors, every other level is kind of idle. And even here, if I look at this processor, it's receiving this data, but this one might send it, but what use is it to send it early? Because this guy is not going to pay attention to it until it finishes receiving the first message, right? And so first this will happen, one. Second, this will happen. Some of the wire time might be overlapped, but overall this guy will be paying attention to that message only after this comes. Then it will go here. And in the meanwhile, yeah, stuff happened here, but it's going to be at least 3 and 4 like that. So given that there is a left to right sequencing happening at each node, I pay attention to my left child, do a receive, then I get the next message from it. Left here could be the first, whichever one I get first. But for analysis purposes, you just get one message, then you get the other message, then you get the third message. Might as well delay this guy. It doesn't hurt if I just put this guy as a child of this here, isn't it? The last one here, if I put it as a child of this here, then by the time I get this guy can get this message, and then it can send it here while this guy is free to attend to it, right? So if I can make my tree skewed from left to right so that there are deeper trees on the left, we might get better performance. And in fact, so that's an example. Yeah, deeper on the right. Did I say left? Deeper on the right, like as in my example, I put this as a child of that, and it had no impact on the time at which this was sending its result up, having one extra node. So the same logic can be applied in various places. So you can do, for example, the same 7 nodes in this fashion, so that this happens at the same time that this happens, at the same time that this happens. Then this sends it here, but it's okay because this guy is sending this in time step 2 at the same time, and this is receiving it, and then this sends it here and this receives it, right? So this is kind of nicer algorithm, and this nicer algorithm can be actually more concretely designed, more regularly designed to be something called a binomial tree. But instead of describing the binomial tree, I'm going to describe to you a hypercube algorithm, and in fact the hypercube algorithm, so, and I'll explain where the name comes from, actually leads to the same binomial tree-like behavior. So what is a hypercube? Even though we are not talking about interconnection topology, there are situations where you want to organize processes in a logical, even though everyone is connected to everyone, I want to think of them as connected in a hypercube, or connected as a grid, or something like that, right? As a k by k by k mesh, like in our matrix multiplication examples. So what is a hypercube? So that's a logical configuration we're talking about first. So a hypercube is very nice because you're all computer scientists, you understand recursion perfectly well, right? So a one-dimensional hypercube is easy to define. Oh, sorry, a zero-dimensional hypercube is a single node by itself, has no connections. Any higher dimensional hypercube is obtained by putting together two smaller dimensional, next smaller dimensional hypercubes and connecting their corresponding elements, right? And so, for example, a 1D hypercube, you put together two 0D hypercubes, one here, and connect their corresponding ones, only one element. And if you take a 2D hypercube, you just take this 1D thing, which is the line here, and another 1D thing, which is the line here, and connect the corresponding elements. To make it a 3D, you take one square, another square, those are 2D hypercubes, and connect their corresponding elements together. Corresponding means identically named. So in this one, if you name them 0, 1, 2, 3, this one you name them in the same pattern, 0, 1, 2, 3, and connect them together, right? Well, up to this, it's just you got a cube, and then after that, what you get is higher dimensional cubes, which is why these are called hypercubes. So you take two cubes and connect the corresponding elements together, and you get a 4-dimensional hypercube. A nice property of hypercubes is that they have low diameter. That means the distance from any node to any node, the worst case of that is small. How small? How many hops do you need to go from any vertex to any other vertex if you are constrained to go only along the hypercube neighbors? I gave you a recursive definition of the hypercube. You can give me a recursive answer. Yes? It's 8? K? Oh, if it's a k-dimensional hypercube, then it's k. Yeah. That's a good. And how is k related to the number of processors, number of nodes? P. P is equal to 2 to the power k, right? It's like a 0-dimensional one, 1, 3-dimensional one, 2 to the power 3 is 8, 4-dimensional one, 2 to the power 4, 16. So it's 2 to the power k, right? And only takes k hops, which means it takes log p hops to go from any place to any place, right? Recursively, you can prove that by saying, oh, assume that in a 1-dimensional hypercube it takes 1 hop. You can prove that empirically in 0-dimensional 0 hops. And then for anything higher, you cross the dimension to go to the right dimension, and then within that it's the same as before. So it's 1 plus what it took on the previous hypercube. So it's going to be k. And so that's nice, logarithmic distance between any two nodes. Of course, we are not building a physical topology. We're just going to use this as a logical structure. So how do you make a logical structure? Given a rank I, given my rank x, how do I find my neighbors in the hypercube? How many neighbors do I have in a hypercube of k dimensions? How many neighbors do I have in a hypercube of 1 dimension? 1. How many neighbors do I have in hypercube of, right? If I'm 1-dimensional, I have 1 neighbor. I am this guy, I have 1 neighbor. In 2-dimensional, I have 2 neighbors. Why? Because in 3-dimensional, I construct 2 previous things and then connect them. That means I have 1 extra neighbor in that extra dimension which connected it, right? And so the number of neighbors is also log p to the base, log p to the base 2, right? And so the diameter is log p to the base 2, the diameter is log p to the base 2, which is k, Okay. Now, how can we use this to do reductions? Oh, but by the way, how do I find those neighbors? Given my rank, how do I know what's the rank of my one of my neighbors, my neighbor in the ith dimension? It's easy. You express my rank as a bit vector, a binary number, and I just take the most significant bit and flip it, and I'll get the neighbor in that dimension. I take the next dimension and flip it. I get from my own ID always. If I just flip one of the bits, I get the neighbor in that dimension, right? Convert it back as a rank, as a number, and I get the rank of the neighbor. So that's also very easy and nice. And now can you think of a reduction algorithm, assuming we have organized all processors in a hypercube, assuming the number of processors is the power of 2, so let's not worry about the edge cases of what to do with incomplete hypercubes. What's a good reduction algorithm? Anything, something. Yes. Yep. Okay, so you just deconstruct the hypercube. You have a k-dimensional hypercube. You know it is made up of 2k minus 1 dimensional hypercubes. You find your buddy, the extra link that was connected, and of course, one of the two is designated as the smaller one, the one that contains 0 maybe. And then if you flip your ith bit, and you were a 1, and the other one is if you flip the ith bit, you get your neighbor in the height dimension. If you were 1 in that bit and the neighbor is 0, then you send. Otherwise, you receive. So you just basically, in one step, what will happen is this hypercube will get squished down by 1 dimension, right? There is no data left in the higher part of the hypercube. Every corresponding element got the data, and you keep doing that for log p steps, and the all data will be at 0. And so these are all completely parallel steps, assuming the links, forgetting the actual topology, but the senders and receivers are all different in each one of the log p steps, right? In one step, everyone from here is sending to everyone here, and that just this and this are paired, and this are paired. There is no two that are paired that are you don't have this contention issue where this guy is getting a message from here as well as here. You don't have that. Everyone is getting a message from one other processor, right? And so in log p steps, there is no reason to add any 2 or any other factor. It's just log p steps, you are done, right? So you can unravel this process as a tree. You can say, oh, that's just a tree rooted here. Its children are this and this and this, and then their children are, again, you can go define their children in the fashion of these hypercube neighbors, and then you will get a tree which is skewed like that to the right, and it does the right thing in terms of without contention, in every phase this communicating pair is completely disjoint with any other communicating pair, and you get the algorithm finishing in log p time, log p to the base 2 time. Okay. Now the completion time of this was k log pk, and the other one is what was kk is the branching factor, whereas here it is just log p to the base 2. So instead of this, we just have log of p to the base 2 as the cost, and there is no serialization going on in that algorithm. It took care of the serialization at each processor. Okay. Okay. So the hypercube, I think what we're talking about is what this picture is going to show. 0. So again, the numbers, if you convert the number to binary, that's what it looks like. Accumulate data from the neighbors until it is my turn to send, and that's all everyone is going to be doing, right? All right, I think you can work that out. Okay, what if n is large? Can you somehow do better than what the previous algorithm suggests? The previous algorithm suggests sending your message to a parent. They are both, Hypercube or not, they're in some sense a spanning tree algorithm. Let's just talk about spanning trees, right? You send your data to your parent. Parent waits for any internal node, waits for its children to send the data and adds it up, and then it sends it up to its parent. In that, can you do anything better than that algorithm? So the case where n is large, an example of that in that simpler molecular dynamics, the one that was not scalable, you're done an atom decomposition or force decomposition, but every processor has a copy of the array of forces for all atoms. And let's say we just want to collect them. Let's say we want to add them up and get the sum. On every processor is what we really want. But the simpler operation is just we want the result on one processor. The straightforward application of what we did before will be k log k to the base n multiplied by alpha plus n beta, that expression, right? That. So if n is very large, you're going to still have k log p to the base k, and we know that that's probably good at 2, 3, 4 or something like that for value of k, and then we're going to multiply that by alpha plus n beta. But you might have a large number of processors, right? And let's say you're doing binary tree, then the depth of the tree for 8,000 nodes is going to be 13. So you have 13 deep tree, right? If you have 1,024 nodes, it's 10 deep tree. How can you somehow, do you see an inefficiency in this algorithm, and do you see a way of fixing it? It's basically, again, a level by level algorithm, right? So you get this huge amount of data to your parent until the parent gets the data from all his children, the huge amount of data. Let's say 10 megabytes of data from one child, 10 megabytes from the other child, 10 megabytes from the third child, and now it's ready to send its message to add them up and send to the parent. But in the meanwhile, all those links in the upper part of the tree, all the processors are just sitting idle. Right? So this is a problem with this algorithm and an opportunity. If n is small, there's probably not that much opportunity to improve upon this. But if n is large, there is a way. When you're sending a large 10 megabyte message, you can do something. Remember, you have a vector of size 10 megabytes. You want the global sum in one place. That means the 0th element of the vector at the root needs to be the sum of the 0th element submitted by everyone. First element of the vector needs to be the sum of the first element sent by everyone. 10 millionth element, well, 10 mega words, 10 millionth element needs to be the sum of the 10 millionth word submitted by everyone. Do I need to wait for all those million or 10 million values to come to my processor before I send them up? Remember, yes?
So are you suggesting that like we send all of our zeros first so that the upper processors can start summing those zeros together, and then we send our first index elements?
Yeah, that's the idea. But that will make it, okay, so here is this guy, and it has a parent there and so on. And here I am sitting with a big long vector, and here is another vector, and 10 million words. And if I send all of that vector here, then this guy sends all of the vector here. This whole link is sitting, this processor, and anyone above it is sitting idle. So instead, what you are suggesting is we send only this value and send this value, the 0th value, and send it here. And then this guy adds it up and sends that up the tree, while this guy is working on sending its second value here, second value, add them up, send it up there, right? So you pipeline, the same old idea of assembly line, pipelining. What is the cost of this algorithm? The cost of this algorithm will be And again, we are assuming a simple binary tree of, well, k-array tree, let's say k log p log to the base p of k. That is what the first one will take. But that's just one of the million words going up. I don't care how long that takes. Suppose I ignore it, then the delivery is going to happen for the next word onwards on every cycle. Right? As soon as the reduction of the first one reaches here, every subsequent one is going to arrive in each receive cycle, right? And but all the messages are going to be of length 1. That means alpha plus n beta, n is 1. But there are going to be lots of such messages, a million, right? Size of the message is, let's say, m. Then it's going to be m times alpha plus n beta. Who cares? Ignore, right? Because n is 1,000 times small, beta is 1,000 times smaller than alpha, nanosecond versus microseconds, and it's only one word that you're sending, so that n is small. So we can ignore this. M alpha, no log p factor because we pipeline it perfectly. So it's going to be m alpha, where m is the size of the message, instead of alpha plus, oh, I see, I should have used the word n alpha, let's say. Alpha plus n beta times k log k. Compared with that, this is just n alpha. Sounds good? Or not? A little algebra. Doesn't look good, right? Because alpha is getting multiplied by n, the size of the message. You are sending a million messages. The root is supposed to receive a million messages. And alpha dominates at that point over beta. Alpha is a microsecond. So you are receiving a million messages, 10 million messages of one word each. It's just going to be, let's say, 10 microseconds for each message, the alpha, then 10 microseconds multiplied by 10, 100, and million microseconds, that's seconds. So 100 seconds is what that's going to take, right? So n alpha is not good because alpha is getting multiplied by the size of the message. Here, alpha was getting multiplied only by k, the branching factor of the tree, and then by the log here. So the multiplier of alpha was very small. Multiplier beta was whatever it was. The beta is gone completely. You can, just one second, you can say log p times beta for that first message to go there, but that's negligible. In fact, alpha plus n beta, but compared with this big thing, that's negligible. So it's n alpha, and that's a problem. But hopefully this gives you a new idea. Yes?
Can we split the difference and send like chunks and
yeah.
around with the chunks?
Who said we have to send one word at a time? Let's send, m words at a time. And instead of sending a 10 megabyte size message, don't send one word message, send a kilobyte message, or maybe 8 kilobyte message. And so packetize this thing in sizes of m, and now it turns out, and I'm not going to do the math, but now it turns out you will get a much better performance, because it's instructive to do the math, but we don't have time in the class to do the math. But what will happen then is that you will get a combination of these two. You're going to get the pipelining across the m messages, across the n over m packets that are going up, and then each one of them is, so over those packets is going to be alpha plus m beta, and so the m size message times, but no log k, because the log k factor is pipelined. So it's basically going to be n over m times alpha plus m beta, and that's how many packets you are pushing. M is the size of each packet, n is the size of the whole thing, and so n over m is the number of things you are pushing, and so that product, that multiplied by that, is all that you're going to incur. Now notice that compared with n alpha, I have n alpha divided by m as the multiplier of alpha, and for the multiplier of beta, instead of n beta k log k, I have m beta, m cancels out here, n beta, right? And so this is n beta times something, and instead it's just n beta there. So, so this is a good pipelined algorithm, and in fact, so we just did on the board what I was doing here in the slides, reductions with large data sets. So n over m pipelined phases, and you can use a k branching factor. So approximately you get alpha plus n well, alpha k m for that, and n over m times beta. So you get that. Instead of this, you get this expression. Okay, I think so. But then you can do something interesting. You actually notice what the leaves of some of the processors in this tree are leaves, and some are internal nodes. How many are leaves? Roughly half, right? Roughly half of them are leaves, and so that's just a property of binary trees. And so, if that's the case, half of them are doing no addition. Reduction involves receiving and doing summation, and half of them are not doing any summation, right? And so your load is imbalanced. So if you actually care about not just the critical path of the completion of the algorithm, but also that whether the processor can do some other useful work while the reductions are going on, like you would do in CHAM++ or with MPI with asynchronous reductions, then it becomes important to balance the load. And a clever way of doing that is to just invert the tree and to basically say, for half of your data, send it along this spanning tree. For the other half of the data, use a different spanning tree. And the different spanning tree can be chosen such that what used to be leaves in the first one become internal nodes in the second, and vice versa. So you can just, a simple way of doing that, which has one flaw, is to just take the rank to be n total number of processors p minus rank is my virtual rank, and build a spanning tree in terms of that. That will just make the last processor the root, and the tree will go down in this fashion, and then it looks like everything is much better, because every leaf in one is the internal node in the other, except the root, except I think one processor gets overloaded. So you can do something clever about that, and you can use that idea for balancing the load and get better performance. But these are the kinds of things that you do. I'm going to skip the topology aware algorithm for now, and come back to it a bit later after we have done some interconnect. All right. So the question now is slightly different. The question is not the broadcast and reduction algorithms. We are now talking about actually, in reality, how are the processors connected? They are connected in such a way that when you say a send call in MPI, and you name any other rank, doesn't matter what the rank is, the data will go to that process, that rank. That means underneath, the hardware and software somehow is making sure to give you the illusion that every process is connected to every process. Every physical processor is connected to every physical processor. How does it achieve that? You still have to actually build a network to make that happen, right? At home, you might connect them all together to one router, and then they are connected. But again, the home routers have one problem. Anyone knows what the problem is? If you actually connect 20 nodes at home, or 8, you bought an 8-node router. If I'm talking to, if node 1 is talking to 3, node 4 is talking to 5, it actually takes away bandwidth from the others. They have shared bandwidth, many of them. So the more modern switches actually are crossbars where anyone can talk to anyone. But still, the radix is small, right? You cannot put 1,000 of them together on a switch, or you can go and ask for the price of that, and then work your life for getting money to buy that one. Physically, typical switches are 64 radix is kind of the reasonable limit with today's technology. You can do crossbar 64 by 64, anyone can talk to anyone type switch, right? And everything else you have to build out of those. Alternatively, you can build, so this is the reason why you actually have to build an interconnection topology. So this was a shared memory view of thing. Anyone can access the same memory, and so there is no notion of relative proximity, and with NUMA we know there is something. And now what happens here is that When you say PE here, we mean a physical process, a physical node. It may have multiple cores inside, right? Many nodes here connected to the network, and then you can put shared memory on the other side. You can actually make a scalable shared memory like that, and this was one of the approaches that was tried 20, 30 years ago. But again, it's not scalable, and so the distributed memory systems that we are looking at through MPI and so on are systems where there is, each processor has its own memory, and again, whenever I say processor, I mean a node which has multiple cores in it. And then it has access to that memory, and then there are others, and you get to the others by some kind of a network that connects them. So your view is your own memory and the rest of the system, and how is the rest of the system connected. And so there are all these ideas: ring, star, butterfly, mesh, torus, and we're going to look at some of them. And look at what performance metrics exist, what cost metrics exist that differentiate these different topologies. So this slide is from Mike Heath's lecture. Some of these topologies are just academic interest. No one would want to build a network which is a circle or a 1D mesh where you can go from anyone to anyone in p-1 hops or p-1/2 if they're bidirectional, right? And but actually some of the higher dimensional things are just simply recursive constructions of these ideas. So a 2D mesh is really taking a 1D mesh and adding another dimension to it. Right? And so you can recursively define them that way. 2D torus is actually taking a ring, which is the 4-processor ring here, another 4-processor ring here, another ring here, another ring here, and also connecting them end around in that fashion. So basically, a torus is like a surface of a not early enough in the morning for you donut. You can imagine a paper, and you say you want to connect the ends to each other, then you'll connect them in this fashion, right? And you got, so now the last processor vertically connects to the first processor vertically, right? And now you can say, oh, I can do that along this axis as well. Take this ring and bend it so that this end connects back here. Well, you got a donut shape. So surface of a donut, you're going to get processor only on that surface for a 2D torus. So that's a torus. Star is this network here. You have a middle point, and everyone is connected to that point. And crossbar is everyone is connected to everyone else through some kind of a cross connection. Well, this is how the switches are built. So but switches may be like that. You build the networks out of the switches. So we're going to just use this as a building block. What's good and bad about star? Anything good? What is good and what is bad? Yeah.
For bad, in order to get to any processor on the rim, you have to go through that central node, which could cause traffic there.
Right, you're going to get bottleneck at the center processor. The good thing is you can go from anyone to anyone in 2 hops. That's a cost metric, right? Cost metric is average internode distance. And so I told you earlier with wormhole routing, the distance almost doesn't matter, but it matters in an indirect way. For a point-to-point message, I'm sending a message to you. How long it takes almost doesn't depend on the distance because of the wormhole idea, right? And so therefore, as long as my message is several hundred bytes, the time it takes is going to be roughly the same, maybe a few nanoseconds, few tens of nanoseconds or hundreds of nanoseconds apart, but otherwise it's going to be about the same. However, I'm occupying more wires if I go over more hops, and that's going to be contention, and other messages are going to be waiting because of that. And so keeping the number of hops small becomes important for the sake of that secondary metric, contention in the network, right? And so number of hops is small here, but contention is still pretty bad because the way we organized it, right? Okay. I think we talked about Hypercube. You can use it to physically connect, not just a logical organization of processors, but you can actually physically wire them like a Hypercube. which is how some of the initial parallel machines in 1980s were built. Do you see a problem with the Hypercube? A good thing about Hypercube is that the number of the diameter as well as the number of connections is logarithmic in number of processors. That seems like a positive thing. Just think about physical layout. You're trying to build one. What are the issues that you would face? Especially compared with something like a mesh, right? We just organize them in three-dimensional mesh. Everyone, not even torus connections, everyone connected to a nearby grid point. XYZ is connected to XYZ plus 1, etc. One coordinate difference. Compared with that, what is the flaw? What is the problem here? 1 second. Yes. When the dimension is growing, number of dimensions growing, what? Physically very far. Oh, that's just because I drew it that way. I could maybe draw it better so that they are close by. You're saying as the number of dimensions increases, the wire length becomes longer, right? But maybe that's just because how I drew it. Okay, let me keep that thought for a second and listen to your argument.
I mean, we only have 3 dimensions. Like, what in reality? Like, once we start getting like really high dimensions, it's just gonna get complicated. You can have wires.
It will get complicated to wire, but will the wire lengths be long? Yes, they are long. You're correct. And in fact, for the same intuition, we live in a physical world that's three-dimensional. You try to squish higher dimensions into 3, you're going to get wires becoming long. You can think about a mathematical proof of that. But basically, some wires will be as long as the entire machine approximately, right? Theoreticians' distance. So maybe size of the machine divided by 3 or something like that. But some wires have to cross the entire space. And so what's the problem? The wire will go over a long distance and carry the message. Is there any issue with the long distance? Yeah, you need to buy a longer wire. Okay, fine, that's one cost. Yes. If you have a longer wire, is there a longer latency? I mean, talking about speed of light, that's nanosecond for 9 inches. It's like it might add up to like a few hundred nanoseconds, 100 nanoseconds. But capacitances are larger. You cannot drive a copper wire at the same speed as you can drive a smaller wire, right? Simply because it has larger capacitance. In fact, physically, there is a limit of maybe 5 meters over which you can connect these long wires. Above that, you can use optical signaling, but optical is expensive. Optical fibers can be used, but electronic to optical conversion, electric to optical is expensive, and so the wires themselves are expensive, so there is a cost issue. So there is a cost issue, and there is and the distance corresponds to basically that cost. Okay, so we'll come back and visit this. What's the problem with binary tree as a topology? Again, a bottleneck here. Any message that needs to go from here to this half to this half will have to go through the root, and that's a problem. Let me see if I have some analysis of topologies before I just show more beautiful pictures. Yeah. Okay, so I guess I will just show the beautiful picture and not explain it. So this is actually, maybe I'll explain. Without explanation, this is nothing. So this was the topology of the dream machine that IBM was going to build for Blue Waters. So the name Blue Waters is that way because IBM was going to build it. That's where the blue comes from. That's deep blue. That's IBM's logo. And so the Blue Water machine design came there, and they had the contract for like whatever, couple $100 million. To build the machine. We were all working on it. I was part of the team, my student staff, they're all working on. The machine was 6 years or 5 years in future when the contract was made, 4 to 5 years actually. 2006 is when NSF came up with the specification. Then we were working with IBM on their virtual design to optimize our algorithms. And the first nodes were delivered here at the facility where the Blue Water sees, and we were all very happy. They look really nice as promised. performance was pretty good, and that's the time that IBM decided they're not going to do this. So I don't know if I'm not privy to all the higher level details, so even if I say something here, it's not, the details of that are up in someplace else, but it is public that IBM walked out of that contract, basically leaving aside, just they didn't get any money for the work done up to that point either, I know, as far as I know. And so, but that machine would have been really, really nice. And because it had this interconnection topology, not because it's beautiful, but look at the connectivity. This is a supernode. A supernode had 32 multi-chip modules, quad chip modules. Each one of those had multiple nodes in it, and they were fully connected. There was a wire between every pair of things there, right? And there's some physical details that are not important here. And then every one of those switches was connected, had some number of connections to the other such supernodes, right? And so if I'm here and I want to go to that particular one there, then I know which one of my nodes I need to go to, one hop. Then I cross over into that supernode, one hop. And then within that, I go to where I want to go, one hop. 3 hops, I can go any place to any place in a machine that was humongous. 256 supernodes, and I don't know what the other numbers were, I forget. But there are like hundreds of thousands or tens of thousands of nodes that you could connect just with 3 hops, right? And so this is a Perks network, and it's an example of a class of topologies called the Dragonfly topologies. The modern Cray machines, the Blue Waters we have now, is not as modern a machine. It uses a 3-dimensional torus, but the newer Cray machines use a Dragonfly class technology interconnect, where the number of hops is not 3, but it is 5. Okay, and all right. So how do you compare the interconnect topologies? For things to work, you must have a connection from everyone to everyone, and they must be physically viable arrangements. You know, you can't do a star simply because you cannot connect a star of 1,000 processors. How will you have 1,000 connections coming out of one? And then they should be economically affordable. And for things to work well, rather than just work, so you want intermediate routing. When data goes from here to there, it stops at some intermediate stops. Those stops should not depend on the CPU that's doing the useful computation of the application. They should just happen in the switches themselves. Path length should be reasonable, and it should be easy to calculate path from one process to another. You can make a very complicated topology, but if to calculate the route, if I get a message and say, okay, this is a flit, where should I send it? Based on the destination address, if I cannot very quickly make that decision, then I don't have a good topology. The routing must be very simple. So the topology is for us is a graph, V and E, where V is the set of vertices. Vertices can be a processor or a router, and E is the edge, the connections between them. Now we can talk about degree, which just defines some vocabulary, and then maybe just 1 or 2 examples, and then we'll stop. Degree is the maximum number of edges incident on a vertex, right? What's the connectivity? Distance between 2 vertices is how many edges is how many hops is the shortest path between them. Diameter is the maximum of that previous quantity across all pairs of processors, right? What is the worst pair of processors? What is the distance going from one to the other? That's the diameter. And edge length is the maximum physical length of any wire. How long do wires grow? And bandwidth, well, we'll have several definitions of bandwidth. We can talk about full bisection bandwidth, which is one definition, and we'll probably go by that. I'll talk about that later on. So to judge a topology, you want the degree, diameter, average distance, which is diameter is the worst case. The average is between every pair, compare every pair, get their distance, and take the average of that. Link bandwidth, which is the bandwidth of one wire. And bisection bandwidth, divide the sets of processors into 2 equal partitions. And there are many different ways of doing 2 equal partitions. Take the worst possible way of partitioning them from the point of view of the metric that's coming up. How much link bandwidth is available to data to flow from one side, one half to the other half. How many links cross from one half to the other half? That's the bisection bandwidth, right? You can do a slight variation on it, which is all-to-all bandwidth, which is if everyone is talking to everyone with some k bytes, how long will that operation take to complete? This is related to the bisection bandwidth, but it's not identical to it, right? Okay, so these are the metrics that you can use to understand networks. Now, if you have a fully connected network, everyone is connected to everyone. Its degree is p minus 1, right? P processes, p minus 1 is the degree. What is the diameter? Oh, come on, this is just to make sure you're not given up on the listening. Diameter is 1. You can go from any place to any place in one hop. So diameter is 1. Average distance, therefore, is also 1. Total links, there are how many wires are there in this network? Roughly p square. Everything is connected to everything else. That's p times p minus 1 by 2 if you don't count both directions. And bisection bandwidth, well, divide it into any half. It doesn't really matter. They're all symmetric. P by 2 processor on one side, p by 2 processor on the other side. How many links cross that those two halves? Well, everyone has connection. Everyone here has a connection to each one of them here, and there are p of 2, p divided by 2 here, and p divided by 2 here. So it is going to be p square by 4, right? Everyone here, that's p by 2. 2, everyone here, p by 2, that's p square by 4. And each one of that many links, and each link's bandwidth is b, so the bisection bandwidth is going to be p square by 4. So does this look like an overkill? Yeah, p square wires. That's what makes it an overkill. The wire cost and connectivity cost. P, how many connections, how many NICs do I need? Network interface cards at each place. P minus 1. That's just infeasible, right? Chains at the other extreme. Here is a long one-dimensional chain, no end-around connection. What is the degree? How many connections does each processor have? Very quick. 2. What is the diameter? 2, because everyone has 2 wires coming out of them. Yeah, okay. Diameter is the longest distance is between this guy and this guy, which is p minus 1, right? So diameter is p minus 1. Average distance, you have to do a little careful calculation of all sums, right? From distance from I to j, where I and j vary over, I varies from 0 to p minus 1, j varies from I to p minus 1, and you will get the sum of all distances divided by the number of distances you calculated, and you will get an approximate thing which will be approximated to p by 3, right? And then bisection bandwidth is easy. You cut it off in the middle, and there is only one link crossing it. So the bisection bandwidth is 1b. Yes.
So the bisection bandwidth, do we have to split it down the middle, or are we just picking the partitions? Could I say every other node is in one of the partitions of the bisection, and then the other?
You are supposed to take roughly equal size partition processors. So if you think there is a weak link between one and everyone else, that's not enough. You still have to take half of the processors on one side, but you can take the worst case of that.
Yeah, but can I say that one partition is if we number these 0, 1, 2, 3, 4, 5, the even ones are one partition and the odd numbered partition is the other? Or does it have to be like you said here, you're kind of just splitting it?
It's a good question also from the point of view, if you actually do that, if you put odd ones on one side and even ones on the other side, the number of wires crossing them is b. That's not b, that's p almost, right? P by 2 or something like that. It's pretty large. Everything is connected to everyone. And so that's not the worst case of it. That's the problem with it. You want the worst case, which means the smallest bandwidth between the two halves. Okay. So I think it's a good exercise to try these things for a two-dimensional mesh. The degree is 4, and you can see what the average distances are and so on. But I want to go show you one other thing and then stop. Actually, maybe I should stop here. Okay, let's just stop here. I'll talk about Moore graph next time.